Notes in first. So I don't have my notes with me right now, but as soon as I got done with the talk talk, I sent you the notes on my email. Sorry, I forgot she's loose today. Is this his chocolate?
I don't know.
I don't. Come on. Come on, Luna. Come. This is for the chocolate. Oh my God. I really it's so hard. Unfortunately, I'm not used to it, but about 7 or 8 out of 66. Which makes me sad. That one has some now. I didn't know they both have some. That's cool. Mine I knew did because I brought it.
Okay, so
yes. And did you, am I correct in thinking that you said you wanted to try to go to that thing up in DC for Adam Scholars?
yes, I did.
It's middle of September. It actually looks pretty cool. So
Yes, I would be interested. I know right now, so because my dad is actually, he's decided to go back into school because he's wanting to become a nurse.
Oh, yeah?
So
where are you going?
My Pell Grant right now isn't showing that it's going to be accepted, but he's got to do his, because he did his FAFSA for the summer. He said he's got to do his FAFSA for next fall.
Yeah.
And so it should like change.
We'll have to see. Iron up there. What is it going on? Hi. Where are you going? Get back to your bed. Let's go. Okay, folks, let's go ahead and get started. Are you going to be difficult? Do I need to put you on the leash today? I know. Come on. You know what you're going to do right now. Sit. Down. Stay. Okay, so today what we're going to do is we're going to pick up briefly where we left off on Monday with solubility product, but that's because it does lead into the common ion effect, which hopefully after finishing your lab is not going to be that complicated. But we'll go over the common ion effect. I want to take a moment once we get into the solubility and then the common ion effect to really explain what the numbers mean, because not only can they describe the amount of solid that dissociates, they can also describe the concentrations of the reactants before a precipitate occurs. So there's a couple of different ways we can look at this. After that, we are going to get into entropy. As I introduce entropy, I am also going to remind you of enthalpy, which you learned in college chemistry 1. Specifically, we're going to focus on, when I get to that point, we'll focus on enthalpies of formation. Just like I said, basically getting your mind back in gear, because we will need enthalpy and entropy for Gibbs free energy. Okay, so what we're going to do is we're going to start with the question of calculating the molar solubility of calcium fluoride at 25 degrees Celsius. And we're going to look at it in 3 different solutions. The first solution we're going to look at it is going to be in pure water. The second solution we're going to look at is going to have the calcium fluoride dissolving in 0.010 molar of calcium nitrate. And the last one we're going to look at is going to dissolve that in 0.010 molar potassium fluoride. Okay, so this first problem in this set is just like what we were doing on Monday. You will take the calcium fluoride And that calcium fluoride solid is going to be allowed to dissociate to form calcium ion and fluoride ion. Now, for every 1 calcium fluoride, you get out 1 calcium and 2 fluorides. Now, in pure water, we're just worried about the calcium fluoride itself, which is a solid initially. And there will be none of the calcium and none of the fluoride present. As time progresses, some calcium fluoride will dissociate, but it's going to be a very small amount. You're going to make 1 calcium for every 1 calcium fluoride that dissociates, and you will make 2 fluorides for every 1 calcium fluoride that dissociates. So then at equilibrium, you're still going to have solid calcium fluoride. We know that because the KSP for calcium fluoride is extremely small. The KSP for this calcium fluoride is equal to 3.9 times 10 to the minus 11. So it's an extremely small number. So we know that there's not going to be an appreciable amount of dissociation. So most of it's going to be solid at equilibrium. But you will have a tiny amount of the calcium and you will have twice that concentration of fluoride. Now, writing an equilibrium equation for this, you will have your KSP is equal to the calcium concentration times the fluoride concentration squared. So our 3.9 times 10 to the minus 11 is equal to X from the calcium and 2X from the fluoride, and the 2X is squared. So 3.9 times 10 to the minus 11 is equal to X times 4X squared, because you do have to square both the variable and the value. So in other words, 3.9 times 10 to the minus 11 is equal to 4x cubed. Luna? So x cubed is equal to 9.75 times 10 to the negative 12. So x comes out to be equal to, come here, 2.14 times 10 to the minus 4. Come on. Get walk around. So this, folks, anytime you solve for x, x is the molar solubility. Because it's literally describing the molarity of the calcium fluoride that is soluble in water. Any questions? Okay. So let's look at part B. In part B, we were dealing with 0.01 molar calcium nitrate.
first of all, calcium nitrate, according to the solubility rules, is completely soluble. So calcium nitrate is going to dissociate entirely into calcium ion and 2 nitrate ions. Initially, you have 0.010 of the calcium nitrate. You have none of your calcium, none of your nitrate. Because calcium nitrate is entirely soluble, you will lose 0.10 of the calcium nitrate. Because calcium is formed in a 1-to-1 ratio with the calcium nitrate, you will make 0.010 of the calcium. And because the nitrate is in a 2-to-1 ratio with calcium nitrate, you will make 0.020 of the nitrate. Solubility rules, which you will be given. But nitrates, acetates, perchlorates, bicarbonates, they're typically soluble all of the time. So when it's all said and done, you'll have none of the calcium nitrate. You have 0.010 of the calcium, and you have 0.020 of the nitrate. Another way you're going to be able to tell what is and what is not soluble is if it is an insoluble salt, you will have a KSP. If I give it to you and there's no insoluble, if I don't give you a KSP for that substance, it's soluble. That may help also. Now, if you look at the question, that calcium fluoride that we started with was being dissolved in that calcium nitrate. Oops. In other words, we have the ion calcium in common. So while we do still start out with solid calcium fluoride, instead of starting out with no calcium, we now are starting out with 0.010 of our calcium and none of our fluoride. For every calcium fluoride you lose, you will gain 1 calcium and you will gain 2 fluorides. So that at equilibrium, we still have solid calcium fluoride, but we're going to have 0.010 plus X of our calcium, and we're going to have 2X of the fluoride. Now, if you'll recall, our equilibrium expression based off of the reaction was that the KSP is equal to the calcium concentration times the fluoride concentration squared. So our KSP is equal to 0.010 plus X times 2X squared, where our KSP was specifically equal to 3.9 times 10 to the minus 11. Now, you may recall when we started equilibria, we talked about an assumption that could be made about the dissociation of a substance when you had a very small equilibrium constant. If you have a very small equilibrium constant, the amount of dissociation is going to be extremely small. In water, if you look back up here, in water, which was pure, it was 2.14 times 10 to the minus 4. When you add a common ion, you can expect that number to go down. So what that means is that you can ignore that X, which causes this formula to become much more simple to solve. So it's 3.9 times 10 to the minus 11 is equal to 0.010 times 4x squared. So we take our 3.9 times 10 to the minus 11, divide it by 0.04, and then we take the square root of that number. And our X in this case is going to be 3.12 times 10 to the minus 5. Now, anytime you make that assumption, you should always check to make sure it's less than 5% of the original concentration. So if we have 0.01 as our concentration, is 3.12 times 10 to the minus 5 divided by 0.010 times 100, what does that come out to be? You can guarantee that it's going to be less than 5. So the assumption will be valid. Because it's less than 5%, I should say. Actually, just to have it there, 0.31%, just so you have the value. So our assumption is valid, and that way it made our life a lot easier. If for some reason you do the math and that comes out to be greater than 5%, that means you can't make that assumption. But I would say probably 99.9% of the time with respect to solubility products, you'll be able to make that assumption. So let's look at the last piece. In that one, I gave you calcium or potassium fluoride. Again, potassium fluoride is a completely soluble salt, dissociating into potassium ion and fluoride ion. We were given a 0.010 molar potassium fluoride. You would have had none of your potassium and none of your fluoride. But because potassium fluoride is a completely soluble salt, it's going to dissociate entirely. For every 1 potassium fluoride you will get out 1 potassium, and you will get out 1 fluoride of the exact same quantity. So that when it's all said and done, there's really not any potassium fluoride. No, what there is there's 0.010 of potassium and 0.010 of fluoride. Now, again, but we were looking at the impact that has on our calcium fluoride dissociation. Calcium fluoride is still an insoluble salt. It is going to set up an equilibrium with its calcium ions and 2 fluoride ions. In this particular case, you have fluoride in common. So you do start out with solid calcium fluoride. You don't start out with any calcium this time, but you're going to start out with 0.010 of the fluoride. You're going to lose X amount of calcium fluoride. For every calcium fluoride you lose, you're going to make 1 calcium, and you're going to make 2 fluorides. At the end, you're still going to have solid calcium fluoride, but you're going to have X amount of calcium. You're going to have 0.010 plus 2X amount of fluoride. Developing our KSP expression, the KSP is equal to the calcium concentration times the fluoride concentration squared. So our 3.9 times 10 to the minus 11, that's equal to X times 0.010 plus 2X. Again, we're going to make an assumption. We're going to make an assumption, oh, that's squared. We're going to make an assumption that the 2X is going to be negligible compared to the 0.01. This is where it's these types of problems where that assumption is extremely useful. Otherwise, you're going to come out with a cubed equation. It gets hairy quick. So in other words, 3.9 times 10 to the minus 11 is equal to X times 0.01 squared, which should be 0.0001, if I'm not mistaken. Nope, I did it wrong. There, yep. 0.0001. So your X comes out to be 3.9 times 10 to the minus 7. Folks, I know that's less than 5%, so that's valid. Now, what does all this mean? Let's get into actual meaning. Back in chapter 12, second chapter of the semester, I think it was, we talked about saturated solution and unsaturated solutions. The other option, yes, we also talked about supersaturated, but that takes a special set of environment. Our other option would be, in this case, a precipitant if we don't have that special environment. So with respect to our calcium fluoride, if you just have calcium fluoride, if it comes out equal to the KSP, then it's going to be a saturated solution, because that is the maximum. That if you combine these two ions together, that's when you would hit a saturated solution. If you wind up going less than the KSP, you're going to have an unsaturated solution, meaning there's not going to be any solid present. If you add calcium ion and fluoride ion together from other compounds, again, if you add the calcium and the fluoride together from other compounds, If it comes out less than the KSP for calcium fluoride, you're still not going to have any precipitate. It's only if it comes out greater than the KSP that you'll get a precipitate. No. I was asked, do you get a precipitate with saturated solution? The answer is no. No, we're talking about when you come. So again, if you took calcium from calcium nitrate and fluoride from potassium fluoride, when you combine those two, if you take the concentration of the fluoride times the concentration of the calcium, if it comes, and you actually do the math, if it comes out less than equal to the KSP, it's going to be saturated. But if you combine, for instance, if you combine 0.01 times 0.01, so let me explain this way. So let's say I have 0.010 calcium ion, and I combine that with 0.010 fluoride ion. Calcium fluoride is what we would do is we calculate the Q for the calcium fluoride, which Q is calculated just like K. So it'd be the calcium concentration times the fluoride concentration squared. When you do so, if you plug in 0.010 times 0.010 squared, you will get out 0.000001. Or in other words, that is 1 times 10 to the minus 6. Because that QSP of 1 times 10 to the minus 6 is greater than the KSP of 3.9 times 10 to the minus 11, you would get a precipitate, meaning you can't add equal concentrations of those values together. Does that make sense now? So what else did we figure out? I'm gonna let y'all catch up with my explanation because I still need to finish out the table. Well, I guess I'll just, no, I really want to make it all together. So up here, let's talk about the other thing we discovered. When we were in (0.01 molar calcium nitrate, what we found out was this molar solubility of 3.12 times 10 to the minus 5. So in other words, the fluoride concentration has to be less than, or has to be, if it is equal to I'm getting there. It's okay. I've gotten where I'm used to this now. Okay, thank you. I've got one on order. Mine disappeared in lab. In case anybody accidentally picked up 2 calculators. So if you find 2, one of them a plain black calculator, let me know. If the fluoride concentration is 6.24 times 10 to the minus 5, you'll get a saturated solution. Because that's equal to 2x. Anything less than that 6.24 times 10 to the minus 5, you can expect to get the unsaturated solution because you won't have enough fluoride to precipitate it out. And anything greater than the 6.24 times 10 to the minus 5, you can expect to get a precipitate. In our 0.010 molar potassium fluoride, basically, if your calcium concentration is equal to that 3.9 times 10 to the minus 7, that is where you're going to have a saturated solution. If that calcium concentration is less than the 3.9 times 10 to the minus 7, that means you're not going to have reached that point of precipitating anything out. Only if you go past it that you will get a precipitate. That's what these numbers mean, folks. Questions? Oops, oops.
Did the calcium nitrate?
Yes.
The one that was 3.12 times 10 to the negative 5, the lower solubility. Why would that be fluorine instead of calcium? So like, I understand doubling that number because it's 2.
Because we were given the calcium concentration as 0.01.
Oh, okay. All right, so we're figuring out.
So basically that's why we're looking, the calcium concentration according to this would be 0.01. So what would the fluoride concentration have to be in order to reach that point?
So for that first category, just for calcium fluoride, we have to get to the Q, but for the rest of them, it's just 2x every time. It has to be whatever.
Well, it's 2x for this first one because the fluoride was 2x.
Okay.
On the second one, it was just x because the calcium was just x. So it all goes back to your original tables. Be prepared to do the calculations. This test is going to be long enough that there's probably not going to have time for much in the way of writing. If it is anything, I will be giving you, would you expect a precipitate or not? And you circle yes or no, because there's no time for writing. Questions? Okay. So now, where do we stand in everything? The beginning of the semester. Well, let's say take the end of last semester, you talked about gases. Then the beginning of the semester, you talked about liquids. Then you talked about solutions, aqueous. So we were just covering all of our states of matter at that time. Then we got to that kinetics chapter. And the kinetics chapter told you how fast a reaction would occur. The speed of the reaction. After the kinetics chapter, we got into all this equilibria. Regular equilibria, Le Chatelier's principle, acid-base neutralization equilibria, acid-base titrations, buffers, KSPs, all this equilibria. And what that was doing is telling you to what extent a reaction will occur. Now, I'm not a particular fan of the order that the book does it, because I think the next chapter is actually where we should have started. And that is, the next chapter tells you, does the reaction occur in the first place? So we are actually going to start answering questions. Will this reaction occur in the first place? And when I say that, folks, what I really mean is, will those reactants turn into those products in the order that it is written? That's what I really mean. In the order that the reaction is written, will that reaction occur? That's what we're about to answer. That, folks, is answered using thermodynamics. Thermodynamics tells you whether a reaction will actually occur. Now, ultimately, in this thermodynamics, we're going to be looking for delta G, which is known as Gibbs free energy. But before we get to Gibbs free energy, we have to provide you the tools to be able to calculate Gibbs free energy. Meaning we have to have discussed enthalpy, which you already have, which is a delta H. We have to discuss entropy, which is delta S. And ultimately, once we get to through those two things, we can finally get to Gibbs free energy. Which is our delta G. Now, let's talk about the processes. We're going to talk about them in terms of favorable processes and unfavorable processes. Now, the first piece, folks, you should already have the basics too, because it's College Chemistry 1. A favorite, oh, by the way, I've always had students confuse enthalpy and entropy. So one of the things I noticed is that enthalpy actually contains the letter H. And so that's just to help you with the terminology there. Now, if an enthalpy is negative, that is a favorable process. That means that it is an exothermic reaction. And it means that heat is a product of the reaction. The reverse can be said if for an unfavorable process, we are looking at a positive delta H. That is going to be an endothermic reaction. And it means that heat is a reactant. Now, I want to take a moment, you know, we all have our things that we love, and I think enthalpy is kind of fun. So I want to take just a moment and help you to keep all of this straight and understand what it means. If we talk about an exothermic reaction with a negative delta H, what it means is that once we give that reaction the spark it needs, it's going to go. It's going to be a spontaneous process once we give it that spark it needs. Now, the reason, and so that is why heat is a product, because more heat is going to be generated as a result of the reaction than was required for that spark. Now, one way I help students try to keep this straight is I look at the term exit or exo, and every time I think of exo, I think of exit. What exits a reaction? The products. That's why heat is a product for an exothermic reaction.
Yeah, I was like, oh.
The same thing over here. Endo begins with EN, just like enter. And what enters into a reaction? The reactants, and that's why heat is a reactant. So it's my little way of helping you keep the term straight. Now, the signs, that is what really confuses people. The signs are all about what happens to the reaction. Signs are all about what happens to the reaction itself. So if this is my reaction right here, what happens to it? Well, if more heat is leaving the reaction as a product, that means what happens to it is that it goes down, and hence you get the negative sign. Whereas if heat's a reactant, that means you have to keep pounding it. You're putting in a lot of heat. Therefore, what happens to my reaction is that the heat has, the number goes up, and so it's positive. In other words, I always go over this, I'm sure other faculty do too. Positive, negative, they don't mean the same thing as they do in algebra. They don't mean the same thing as they do to a checkbook either. Not entirely. What they mean is what is happening to that reaction. Is it going up or is it going down? So that's my crazy explanation to hopefully help with these signs and these terminologies that you may or may not have gotten in college. Come on. Now, let's move on to entropy. Entropy describes disorder, chaos. We're going to go over entropy in a little more detail here in a minute. But with respect to entropy, a positive delta S is a favorable one. A positive delta S means there's greater disorder in the products. The products have a greater disorder. Whereas a negative entropy is not favorable. And it would mean that there's a greater disorder in the reactants. Let me finish this table and then we'll take our short break. For Gibbs free energy, what you want is a negative delta G. For a favorable process, a positive delta G means that it is an unfavorable process. Now we'll have to get to the entropy and enthalpy to figure out what delta G is, but delta G is the ultimate. And with that, we will take our break. You want to walk around with mommy? Now you can go say hello. Let's go walking. Or jump down. You're more likely to jump down. You don't want that screen, I know. Oh, stretch. Okay. So, now that it's stopped wiggling, you're okay. Got it.
My dog was supposed to be super smart, but he's not. Well, they're all okay. The board's like, it's supposed to be like super smart, but the boy, I don't know. Yeah, so I was gonna say he split his leg like open. That's the goal. He's just running around, jumping around, scared, and all. You're like, you're stupid. How not? He's half quarter collie, quarter black, and quarter black. No, he's so good that he would rather bring his foot out. He would rather use his hair. We gotta get back to work.
Okay. So now we're going to talk about entropy. So I'm going to go back to this picture up here. And we're going to think about it. When I think of entropy, again, I think of chaos. Chaos. And I think about when my daughter was young, probably still is an issue, and her sock toy. And, you know, I'm not quite OCD, but when I get going, I get going. I'd have to put in so much freaking time putting her socks together, rolling them up, putting them in maybe color order if I was really going to get going. And what would happen? How long would it take to get back to chaos?
Not very long.
Basically, the next time a set of socks came out, and there it went. Why? Because nature moves towards chaos. Nature prefers to move towards disorder. You have to put energy in to make things organized. It's not fun. It automatically moves away from it. So that's what we're talking about with entropy. Now, so let's talk about things that will impact entropy. The most important one, the first thing you should look at, period, is the state of matter. Let's think about this. If we have a solid, everything is in a very nice 3D array. And no, I'm not going to try to draw it 3D. When we move to liquids, they're a little less organized. But because of those intermolecular forces, they're still pretty close together. When we move to gas, well, that's probably the most disorganized thing we can get. Because they're moving every which way. They don't care where they're at. They're just going to move until they bump into something. And then somewhere in the middle here is where we're going to find aqueous. And we find aqueous because basically aqueous means that, yeah, we got a liquid, so it's kind of organized, kind of not. But when you got something that's aqueous, it means you also have other things present. It's not just one thing. So, with respect to entropy, your gases would be moved towards the positive side of entropy. Where's your solids? They're not very favorable. Now, the next thing you're going to look at, though, is your stoichiometric coefficients. Your number of molecules. By the way, just as a note, I only do this one if I cannot tell the entropy based off of state. Then I'll look at that one. And basically, this reminds me of having 2 people in a classroom compared to 50 people in a classroom. You know, when I look at the desks, I see phones, calculators, markers, keys. I mean, but if you only have one person, there's going to be only a little bit of stuff. But if you got 50, we can spread out. It's all good. But when you're talking about your number of molecules, that means if we're looking at this, the fewer the molecules, will create a unfavorable process. Whereas the greater the number of molecules, we get to favorable. So let's look at how you might see at least a portion of this on the exam. Predict the sign of delta S in the following processes. We'll start straightforward. Let's go the creation of steam. This is definitely a positive delta S because we have gas in the product. And that's a more favorable state of matter. While we're playing with water, let's play with water in another form. Let's take water at 25 degrees Celsius. Let's make it water at 75 degrees Celsius. Positive. Again, it's going to favor the products because if we think about what's going on with water, I mean, 25 degrees Celsius, it's just wiggling around. As it gets higher and higher in temperature, it gets crazier and crazier. So you would expect more chaos. Okay, let's look at the formation of aluminum oxide. This one would be a negative delta S because you have a gas on the reactant side. So there's greater greater chaos on the reactant side. One more. Yes. That is a valid reason. So the question is, would the fact that it also is less molecules be a reason too? That is actually a valid reason as well. But the fact that you're going from something that has a gas to something that doesn't have any gas, that's still going to be the predominant issue. Okay, one more. Let's take H2SO4 aqueous. And we are going to take that strong acid. What am I doing? And we're going to allow it to dissociate entirely into its ions. So what are we looking at? This one is a positive delta S. This is the prime example of when counting the number of molecules happen, because over here you have one molecule, whereas over here you have 2 + 1, or in other words, 3 molecules. So that's how we can take a reaction and simply look at the reaction. But for Gibbs free energy, we're going to need to be able to calculate the entropy. Folks, you already got it in your toolbox if you remember anything about Chem 1. It's okay. So back in Chem 1, you learned a calculation for the enthalpy of reaction. It was the sum for the products of the number of moles times the delta H of formation minus the sum over the reactants of the number of moles times the delta H of formation. Now that you're seeing it, do you recognize it? We'll be using that equation when we get to Gibbs free energy. Now, the nice thing, folks, is that if you know the equation for enthalpy, you know the equation for entropy. Because the entropy of a reaction is equal to the sum over the products of their number of moles times their individual entropy minus the sum over the reactants of the number of moles times their entropy. Now, again, I am going to go over something that I know I go over in my class in Chem 1, but I also want to just make sure everybody, I can't remember, I think I've even done it in here, but still. Folks, anytime you see the delta, no matter what, delta always is final minus initial. And I'm saying that because as an instructor, that's one of the errors that I always see is students reverse the formula. So that's why I'm going over it. So delta is always final minus initial. So delta T is the final temperature minus the initial temperature. Delta V is the final volume minus the initial volume. Delta H is the final minus initial. But when you're looking at a reaction, what is the final? The products minus the initial, which are the reactants. And so that's why it's in the order that it is in. Okay. You will be given your enthalpies of formation and your entropies for materials. You're not expected to memorize any of that. Now, I may give it to you as a table. And so I do want to make sure there is one other thing that I say before we get into one. When you're looking up your enthalpy or your entropy, make certain you pay attention to the state of matter. Because the entropy and the enthalpy will change depending upon the state of the matter. The other thing, though, that you did not hear because, well, this is the first time on entropy. If you will recall, enthalpies of formation for elements in their standard states is 0. So O2 would be 0 for enthalpy. H2 is 0 for enthalpy. That's not the story for entropy. Every single thing out there is going to have an entropy. So even elements in their standard states have entropy. So let's quickly, I think I can look at the reaction that we started with, which was H2O liquid going to form H2O gas. We will be picking up with more of this, so don't worry. If I look up their entropies online, in a textbook online, you'll find that the entropy is in joules per mole Kelvin. By the way, that little knot, that little circle I keep drawing up at the top, that means in standard state. For water in liquid form, it is 70. For water in gas form, it is 188.8. So if I want the entropy of the reaction, it is going to be the products which is 1 mole of H2O gas times its entropy of 188.8 joules per mole Kelvin minus the reactants, which is 1 mole of H2O liquid times the 70 joules per mole Kelvin.
David, husband, you're married.
Sorry. I'm not out of class yet. Or in other words, in this case, it's 188.8 minus 70. So it comes out to be 118.8 joules per Kelvin. This is your entropy for this reaction. Because I did not list a sign, it does mean that it is positive. So we are talking about a positive delta S. So it is a favorable process, which we just now proved with calculation, what we determined from visual inspection. It is correct. The moles cancel out because it's mole cancels here and mole cancels there. We will be doing these calculations and adding Gibbs free energy to it on, well, technically tomorrow to some degree, but for certain we'll be going over it on Monday. Calculator. I didn't even have to use it after I got it. Thank you, though. I actually have one being delivered because mine disappeared.
Like today, or do we need this tomorrow?
No, it's supposed to come in. I don't know when, but it'll be good. You too.
Or when you can't make the assumption, you go to acts.
Yeah.
And then you go to with this.
Yeah.
You can pick what order.
Oh, I know. I just
I was because I ran it and it was like point.
It shouldn't have been a big difference though.
Yeah, it was like nothing.
Yeah. Right. Usually I just on KSPs in particular, for acid base, it's always going to use a quadratic. So I go ahead and do it with those. But with KSPs, you have to be very low concentrations for it to make any difference.
I know I asked you this yesterday, but for the scientist one, like I was wondering how you would see the PowerPoint, because whenever we click the PowerPoint link, it downloads like on our device. And so
then you're going to upload it to email.
Okay, so I just email it to you.
Send it as an attachment.
Okay, sounds good. I was just making sure. I need the bonus points, so thank you.
Quick question. I emailed you all my extra credit stuff.
Yes. The only thing I haven't, the only thing I don't think I put in yet is the famous scientist piece, because I'm going to put them all in at the same time.
But you did get it.
Yes.
Because I figured something just didn't attach.
No, I got all of it. I'm putting in all the famous scientist ones all at the same time because of how I'm having to keep track. I don't have a sheet of paper, in other words, for each person.
Oh, right. Okay.
So I
You're
can't
just
keep
filling in
track
the
of who
chart.
I've done.
Okay.
So I'm just putting a check mark by names as they send them to me. And then I can put it in all at the last minute.
Okay, sounds good. I just didn't know.
No, I got it. I just, nothing's missing, just me trying to keep straight at who's turning what. Okay.